Let's look at an example of a power series. And we're not going to be incredibly rigorous, but whenever I encounter something that might be an issue, I'll at least mention that this is something we have to be more careful about, and we're going to go back and develop those skills. So super important function, the natural log of x or ln of x. And we couldn't do this around x equals 0. It wouldn't make a whole lot of sense because it has an asymptote there. The function has to be nice. It has to have all of its derivatives, in fact, at the point of evaluation for this to make sense. And right away, we can see that this project has to fail to some extent. We can't possibly create a nice function, a nice expression like a power series, like an overgrown polynomial, supposed to have all these nice properties, can't possibly work for all x because ln x doesn't work for all x. In fact, 1 unit away from where I'm going to expand, it goes haywire. So you don't always have that that warning just from the shape of the function, but this is definitely telling us don't be too cocky about what you're going to get. Okay, so I'm going to show you 2 ways to get this. Might as well do it as an example of the Taylor process, but there's sort of a slicker way to do it later. And so, but this isn't too hard. F of x is log x, just to have it all together. F of 1 is 0. F prime of x is 1 over x. F prime of 1 is 1. F double prime of x is minus 1 over x squared. F double prime of 1 is minus 1. Remember, we're looking for patterns here. Third derivative, minus 2 times minus 1, you get plus 2 over x cubed. So third derivative at 1 is equal to 2. Fourth derivative, minus 6 over x to the fourth. So fourth derivative at 1 is minus 6. Let me put it over here. I don't want to squeeze it too much. Fifth derivative, we're going to find the pattern real quick, is minus 24 over x to the fifth. I think we can probably see it at this point. F fifth derivative at 1 is minus 24. If I do another one, I'm going to get a minus 5. So the sign's going to switch again, and I'm going to get a 5 times 24. Or in other words, 5 times 4 times 3 times 2 times 1. And this was 3 times 2 times 1. So let me rewrite this. This is 2 factorial. This is minus 3 factorial. And I got the sign wrong. This was a plus. Yeah. And that's 4 factorial. Okay, so hopefully you noticed that. Okay, so it looks like the nth derivative at 1. Notice the 5, we get a 4 factorial because there's a little bit of stutter here. And we've got a sign change. So let's see, it's going to be an n minus 1 factorial, and then minus 1 to either n minus 1. Actually, you know what? I like calling this k, because I've been reserving n for usually like where we stop the process, and here we're not going to stop. Let's see, so minus 1 to the, let's see, when this is 3, it was plus, when it was 4, it was minus. So it's going to be k minus 1. Hopefully you can read that. Okay, so that's our information. That's really all we need. That's the punchline from all that. Wasn't too bad. And so our Taylor series is going to be 0 plus, I guess I should have saved the explicit stuff, but it was a 1 and then a minus 1 over 2, because it was the 1 was that, it was a minus 1 was the last one, was that one. And then plus, it was a 2 over 6, or 2 factorial over 3 factorial, x minus 1 cubed, minus 3 factorial over 4 factorial. And so I'm just doing, these signs are changing each time, and it's the previous factorial, 1 less than the power. Let me write one more out. We got up to 5, plus 4 factorial over 5 factorial, x minus 1 to the 5, minus, and then we'll put dot dot dots, and hopefully the pattern is clear. Well, so we get the 0 doesn't do anything. X minus 1 minus 1 half x minus 1 squared. Can't really simplify that. 2 factorial over 3 factorial just cancels down to a plus 1/3. 3 factorial over 4 factorial cancels down to a minus 1/4 plus 1/5. So we see it's a very simple pattern in the coefficients. There's an alternating sign, and I'm going to actually kind of fix that or do it in a way that kind of shows that in a different way pretty soon. But this is the Taylor series for log x. Now, that doesn't necessarily mean, we haven't proved that this necessarily, even if we take the limit and sum the whole thing as an infinite summation, that it really calculates natural log of x. To be very, very careful about that is a little subtle and requires some real work with the Taylor remainder story. And also, we know that it's ridiculous to say that if x is 0 or negative. There is no thing it can be equal to. So there's no way that this, we're not sure whether this actually even works when x is less than or equal to 0. But whatever it does, it certainly can't be equal to log x. So there's an issue of where does this converge, and if it, for the x's that it converges to, for the x's for which it converges, does it actually converge to the function we were actually trying to evaluate? Okay, so, but let's be a little bit bold and say we hope log x equals this on some subset of 0 to infinity, positive reals. Okay, and it's going to be interesting actually what subset it actually works on. So this was a natural thing to do. A equals 1 was a very natural base point, and wasn't that really that hard to get these coefficients and get this expression. The x minus 1s are a little bit annoying, repeated over and over and over again. And there's another way to deal with that, and that is instead of having x minus 1s here, maybe put something in here and modify the function a little bit. And it's going to be nice. We can also deal with the alternating signs. Not that they're horrible, and they're very common, but we can do it a little bit prettier. If we just modify the function a little bit, let's flip and shift it and actually say, let's take ln of 1 minus x, and then we can use a equals 0, because that's going to be the base point. That's a very natural base point. So that has flipped and shifted it so that it looks like this. Now the bad point, the bad x, where the asymptote happens, is x equals 1. And actually the good x's for this are smaller than 1 and including negatives. So that's my new function. Okay. And I could just substitute in 1 minus x everywhere I saw x in the previous power series, and that you could get the answer pretty quickly that way. But let me show you how there's a slicker way to do this. And that is just take one derivative. You get 1 over 1 minus x, and then with a minus sign for the chain rule. And now, let's see, what is 1 over 1 minus x? That should look really familiar. Especially if I change the variable just a second, the variable name for a second, 1 over 1 minus r. I claim that is just the sum of 1 plus r squared plus r cubed plus r fourth. This is the famous geometric series. Well, so I'm going to change it back to x. Doesn't matter what the letter is. So in fact, without any Taylor stuff at all, and there's lots of other ways to get series besides the Taylor mechanism, we have a power series expression for 1 over 1 minus x. So again, because I'm not being super rigorous, I'm not going to worry about how would you prove this one explicitly. I'm assuming you're at least somewhat familiar with that this is a true fact. And let's see, where was this true? It's true when x is smaller than 1 in absolute value. If x is 2, you're going to get 1 plus 2 plus 4 plus 8 plus 16. You try to sum those up and take a limit, it's just going to go to infinity. If x is minus 2, you get 1 minus 2 plus 4 minus 8 plus 16. That oscillates to infinity, and that's even worse. Okay, so turns out this is true on exactly a limited region, but notice there's something interesting about that. The base point is now a equals 0. This is a symmetric interval. about a, which happens to be 0 here. So that's interesting, and that's really very, very typical. That's the kind of place that these guys converge. So why is this useful? Well, if you put a minus sign on that guy, it's just minus of all that. That seems pretty tame. And then if I know that the derivative of the function I really wanted the series for is this guy, well, I'm going to be ambitious again. Again, this is a tour of what you can usually do with series without a lot of worries about when you can do it and how to be careful. Let's just integrate both sides. That is going to give me log of 1 minus x. And once again, just like I mentioned differentiating, just dot, dot, dot. If this were a finite degree polynomial, you could totally integrate all the terms separately and then add them up. The integral of a sum is the sum of the integrals. But this is not just a sum, it's a limit of sums. And we're really asking, can we pass that limit through the integral? And that is pretty, a bit dicey, but it does actually work most of the time. And if we assume it works, what do we get? We get minus x squared over 2 minus, note the minus sign, minus x cubed over 3 minus x fourth over 4. Notice the 1, 2, 3 over 2 over 3 over 4, very similar to what we had before. And it's no longer in terms of 1 minus x, it's just in terms of x. So these actually, this formula and the formula we had before are equivalent. So that's a really nice one. And you often see it expressed in this way instead of as a power series for log x around 1, just because this is a little prettier. It's just quicker to write. So it's saying, maybe sometimes we'd rather think about this function. So this has kind of been a tour of an example of a really important power series. The fact that maybe we'd like to be able to integrate term by term in a series. The fact that sometimes we can get series in ways other than Taylor and then manipulate them to get more and more series. And on the flip side, on the sort of the bad news side, the fact that this is not universally applicable. This is only applicable for some small range of x's. This does not converge outside of minus 1 to 1, and so it certainly doesn't equal this. Similarly, that tells us that it's very unlikely to expect this to converge outside of minus 1 to 1, and that is indeed the case, that if you go outside of that region, this is not going to converge either. Again, roughly, not being too rigorous, you can see that by, say, plug in x equals 2 and see if it makes even reasonably likely to converge. Minus 2 minus 4 over 2 minus 8 over 3 minus 16 over 4 minus 32 over 5. These terms are not even getting small. There's no way you can make sense of an infinite sum if these terms aren't going to 0. That's one of the things we're going to say very carefully soon. But this is just nonsense that you could try to make sense of that. And that's all I wanted to say about ln.